Our next circuit of interest is the differentiator, which is very much like the integrator, except the positions of the resistor and the capacitors are reversed. To analyze the circuit again, we will take a look at the currents flowing in both components and observe what happens. The current flowing in the capacitor, I1, is equal to the capacitance times the change in the input voltage divided by change in time. Now, the reason why this is true is because this end of the capacitor is a virtual ground because the non-inverting input goes to ground. That means that this voltage is zero at this end of the capacitor. If the Vin was constant, there'd be no current flowing. So only if there's a change as a function of time, delta Vin over delta t, will there be a current. Otherwise, this expression goes to zero and I1 goes to zero. The second current, I2, is equal to minus Vout over R. And the reason why it's minus is because, noticing the direction of the current again, the output of the op-amp is attached to the negative end of the feedback component. And so that's consistent with the fact that we have a positive current, positive voltage going into the inverting input, and it gets inverted at the output. And of course, we can also note that I1 is equal to I2, and that's because the inputs in the op-amp draw no current. Now, just to digress for a moment, we'll notice that this is clearly Ohm's law. Voltage is equal to current times resistance. But over here, we have a peculiar thing where we have capacitance in the numerator, as opposed to here, the resistance is in the denominator. You may wonder, where did that come about? We also have this delta T. Well, we'll just recall for a moment that the reactance, or the equivalent of the impedance of a capacitor, is equal to 1 over 2 pi Fc, its capacitance. So, putting this reactance into an expression like Ohm's law, you can see right off the bat, hopefully, that if I have a fraction in the denominator, that the C pops right back up into the numerator. So that's why the resistance is in the denominator here, but the capacitance is in the numerator. It's because the reactance is 1 over C. And as for this F, you'll recall that for a fundamental frequency, F is equal to 1 over T, or the period. And again, this is in the denominator. F would pop up into the numerator over here, converting it to time, F of 1 T. T appears in the denominator. So this C comes from the fact that the capacitance is in the denominator in reactance, and this delta T comes from the fact that time is the inverse of frequency. So now let's equate I1 and I2. And so we have C delta V in delta T is equal to minus V out divided by R. Solving for V out. V out is equal to minus RC delta V in divided by delta T. And if we want to express this in a more rigorous mathematical form, we would say V out equals minus RC d dt of V in. So the output is minus RC times the first derivative of the input voltage. So here it is, the defining equation of a differentiator. Now, there is a slight problem with this circuit, and the problem is that as frequency increases, the reactance of the capacitance goes down, and so the gain of the circuit goes to infinity, which means that basically it amplifies high-frequency noise. It's a noise amplifier, and that's very highly undesirable in most signaling circuits. We don't want to boost high-frequency noise. We'd like to limit it somehow. And so there's a way we can modify the circuit to limit the gain and to get rid of high-frequency noise. To do that, we're going to make two slight modifications to the circuit. So again, just draw our op-amp. And what we're going to do is we're going to put a small resistor in series with the input capacitor. And we're also going to put a small capacitor in parallel with the feedback resistor. So we'll call this R1, C1, R2, C2. Now, when looking at these components, we don't want C2 to be dominant during the normal operating region of the differentiator. So we want this capacitor to be substantially smaller than this one, C1, so that it simply limits the high frequency gain, and as the signals go up and up and up in frequency, it does not boost noise. So as a basic rule of thumb, C1, this capacitor here, should be at least 10 times greater than this capacitor here. This should be a relatively small capacitor. And the same thing is true with the resistors. This resistor, we want this to be a small resistor. So another rule of thumb would be to say that the product of R1, C1 should be really equal to R2, C2. So that guarantees that this capacitor will be small and this resistor will be small. Now, what is the response of this thing going to be like as a function of frequency? Well, it's actually quite complicated. So again, we're going to have to go back to Bode type plots. And Bode plot, of course, you'll remember, is the logarithm of frequency. Logarithm of frequency in this direction. And in this direction, it's the gain in dBs, decibels, which is also a logarithmic scale. Now, the beauty of using logarithmic scales is that when we plot functions of this type with exponential components like RCs, time constants, is that they turn out to be straight lines. So the frequency response is going to be very low frequencies. It's going to rise to some maximum, and then it's going to fall. Now, the circuit over here would like to very much go to infinite gain. You can imagine that here. If the gain is R over XC, this goes to 0, the gain would go to infinity. But now we're limiting the gain. We're limiting the gain because we've got a resistor here and a resistor here. So it prevents this capacitor from causing the gain to go to infinity. So the peak over here, the peak gain of this circuit is going to be about 20 times the log of R2 over R1. And the slope in this part, the rising slope and the falling slope, will also have the same relationship, and that is that they will be rising and falling at 20 decibels per decade. That's to say, if we increase the frequency by a factor of 10, the signal output will either rise or fall by 20 decibels. The corner frequency should be about 1 over 2 pi R2 C1, and this one over here should be about 1 over 2 pi R1 C2. And the part of the circuit that we would use, the frequency response we'd use as the differentiator, would be this slope over here. So we start from a very low frequency, low gain circuit to a maximum of about the ratio of the feedback resistor to the input resistor. So there we have it. Calculus, the differentiator, the circuit that measures the change in signals. If nothing's happening at the input, the output is 0. If something's happening here, a lot is happening here.